In section 2 of chapter 4, we want to talk about metathesis reactions, which is a type of reaction that can occur when two solutions of ionic compounds are mixed. Mixtures of ionic compounds don't always react, but when they do, it's typically a metathesis reaction, and that will be the subject of this section. So a metathesis reaction, in general, is a reaction of the form AX plus BY going to AY plus BX, whereby A and B, I'm referring to cations, and X and Y refer to generic anions. And of course, this is a generic sort of reaction. There might be subscripts and stoichiometric factors included, but the general idea is that in this sort of reaction, the cations and anions swap partners. The cation that started with X ends up with Y. The cation that started with Y ends up with X. This is also called a double displacement reaction for fairly obvious reasons, that the two cations are displaced and take on the other opposite anions. Note in particular, and I've highlighted this in red, it's important, if no actual reaction takes place, then it isn't a metathesis reaction because there is no reaction. That is, if all of these species are aqueous, then they're really just floating around as separate cations and anions in solution. Remember, they're all strong electrolytes, so they really exist as ions in solution unless one of them is insoluble. So here's an example of a specific metathesis reaction. Copper 2 nitrate, which is aqueous. It's an aqueous solution, is mixed with an aqueous solution of sodium carbonate, and that forms a precipitate of copper 2 carbonate that's insoluble. It drops to the bottom of the container, and a solution of sodium nitrate. So here's the critical idea. For a reaction to take place, one of either AY or BX, one of the products must be insoluble so that we actually see a reaction take place. And we form what we call a precipitate, which is simply an insoluble solid formed by a reaction in solution that then settles to the bottom because it's more dense than the supernatant fluid. So let's see an example of a precipitation reaction. Suppose I take lead 2 nitrate and I mix it with potassium iodide. Will a reaction occur? So I've grabbed a YouTube video. You can probably find this on YouTube. Let's just take a look. So what we're going to do is we're going to drip potassium iodide from this tube down into this solution of the lead 2 nitrate. Watch what happens when the drop hits the solution. All right, that brilliant canary yellow cloudiness is the formation of a precipitate. It will take a while to settle to the bottom of the container because it's very, very tiny particles, so it takes a while to settle, but each drop that hits the solution forms more of this precipitate. So we clearly have a precipitate forming. Our next question is, which precipitate? So if we set up the reaction in the form of a double displacement, we've got lead 2 nitrate with potassium iodide. It's going to react. If I swap the cations, the potassium is now going to go with the nitrate. The lead 2 is now going to go with the iodide. One of these two is the precipitate. And other than, seeing the label on the YouTube video, which you may have noticed, how do we know which of these two products is the precipitate? Well, in general, there's two ways to tell. First, you do a bunch of experiments, and from the results of the experiments, make logical deductions about what precipitates and what doesn't. And you should see the first lab in Chemistry 171L to see an example of this. You're going to be doing this in lab, going through the logic of how you deduce what is and is not a precipitate from seeing the results of experiments. But of course, many of these experiments have long been done, and the results of them are compiled into what we call solubility rules, which are just a summary, a short form summary of the trends of what substances form precipitates, what substances are not soluble in water, and what substances are. And I've provided a list of solubility rules for you on the Canvas site. Here it is. Looks a little busy. I'm sorry about that. There's only really 6 rules, so let me just go through them really quickly. You can find this in a Word document on Canvas. First of all, soluble ionic compounds. All ionic compounds containing a group 1 alkali metal cation, sodium, potassium, those things, or ammonium, they're always soluble. Always. Doesn't matter what the anion is. All ionic compounds containing nitrate, acetate, chlorate, or perchlorate anions are soluble, regardless of what the cation is. Most ionic compounds containing chloride, bromide, or iodide are soluble, except for those combined with lead-2. That's the case in our example. We have lead-2 iodide being formed, mercury-1, or silver. And also most ionic compounds containing sulfate are soluble, except when combined with calcium, strontium, or barium ions. You can think of those as heavy alkaline earths. They're all in the same group. Or the same group of cations from Rule 3, lead-2, mercury-1, or silver. Notice that's the same as the ions above here. And then we have rules for what are typically insoluble. So most ionic compounds containing carbonate, phosphate, chromate, or dichromate, most of them are insoluble, but notice this is subject to Rule 1 above, that is, unless they're combined with alkali metals or ammonium, which are always soluble. So ammonium dichromate, for example, is soluble, even though most other dichromates are insoluble. And secondly, most ionic compounds containing hydroxide, oxide, or sulfide are also insoluble, except when combined, of course, with alkali metal cations or ammonium, or when combined with calcium, strontium, or barium cations, that is the same heavy earth metal cations that were in Rule 4. So there's really only sort of two groups of cations that have special cases that you have to remember. Lead-2, mercury-1, silver-1, they're in one category, and the other is calcium, strontium, and barium cation, heavy alkaline earth cations, in a second category. So when we apply these rules, of course, we see that the lead-2 iodide is going to be insoluble, so it's going to be the precipitate. If we work through all of these compounds, by the way, we know that lead nitrate will be soluble, aqueous, because all nitrates are soluble. All potassium ion salts are soluble, so this is definitely soluble. We've already gone over the rule for why this is insoluble, and of course potassium nitrate, all nitrates are soluble, and all potassium salts are soluble, so this is super soluble. Solubility is a term that we use to measure the amount of substance that can dissolve in a given amount of solution. So we can measure this in various quantities, and we'll look at units for solubility later. But for example, if the solubility is less than about 1/100th of a mole per liter of solution, we're going to consider the substance insoluble. So the term insoluble doesn't mean that not a single bit of substance dissolves. It just means that so little of it dissolves, like lead iodide. There's not a zero solubility, but so little of it dissolves that it's an insubstantial amount. It just doesn't make much difference in the solution. Finally, let's talk about how we can write these metathesis reactions in three different ways. One way is called a molecular equation. And it's called a molecular equation not because there's any molecules involved, because of course there are not. These are all ionic compounds and there are no molecules. But by writing them as intact formulas, that is, not showing them as separate ions in solution, we're writing them as if they were molecules. And that's why this is called the molecular equation. This is a very common way of showing a metathesis reaction, one that we've already used. I'm just telling you that it's called a molecular equation. It's about how we write it. It has nothing to do with the reaction type. It's a description of the equation that we use to represent the reaction. A second way of writing this is called the ionic equation, or sometimes the full ionic equation. And what we do in this representation is we show each substance how it actually exists in solution. Remember, ionic substances are strong electrolytes, so that when they dissolve, when they're aqueous, they literally exist as separate ions in solution. So lead-2 nitrate exists in solution as one lead-2 ion, 2 nitrate ions. This gives us 2 potassium ions and 2 iodide ions. Notice we do not separate the lead-2 iodide into ions because that only happens when the substance dissolves, and this substance is insoluble, so it does not break apart into ions. But the potassium nitrate does. It's soluble, so we get a 2 potassium ions and 2 nitrate ions. And if you'll notice, let me see if I can get my pen to work here. Notice that we've got 2 potassium ions on the right, and we've got 2 potassium ions on the left. We've got 2 nitrate ions on the right. We've got 2 nitrate ions on the left. Those ions really aren't doing anything. They're not adding anything to the description of what's going on in this reaction. We call those spectator ions. Those are ions that essentially do nothing in the reaction. They're just standing around watching the action. They're not involved in what's taking place to make this a reaction. Okay? So what I've underlined are the spectator ions in this particular reaction. What's left that isn't underlined is referred to as the net ionic equation. It's the summary of what's really happening in this reaction. Now, a lot of times students, when I ask them to write a net ionic equation, what they do is they write the ionic equation, they identify the spectator ions, they cancel out the spectator ions, and what's left is the net ionic equation. And that's one way to do it, but the simpler way to do it, and the more straightforward way, is just to recognize from the original reaction here what's actually taking place. We're forming lead to iodide. Then just write down in the net ionic equation which ions have to be combined to form the actual product and ignore everything else. And that is perhaps a simpler and quicker way of arriving at a net ionic equation.